Hello everyone, I'm Akash. In today's video, we will solve an interesting question on real analysis from CMI MSc PhD Entrance 2023 exam. Question is, let f from closed interval 01 to R be a continuous function and E subset of closed interval 0. Which of the following statements are true? We have given 4 different statements and we have to verify which of these statements are true. So let's begin the solution. We will examine one by one each of these statements. So let's start with a statement in A. If E is closed, then f of E is closed. Is this a true statement? Yes, this is a true statement. To prove it, since E subset of closed interval 0, 1 is closed, and as closed interval 0, 1 is a bounded set, so E is also a bounded subset of closed interval 0. So overall, E is a closed and bounded subset of closed interval 0. So this implies E is compact. Okay. And by properties of continuous function, we know that continuous function maps compact set to a compact set. So this implies the image of E under F, that is f of E, is compact subset of codomain, and here codomain is R. So f of A is compact subset of R. And we know that compact subset of R are closed and bounded. So this implies f of E is closed. Thus, if E is a closed, then f of E is also closed. So the statement in A is a true statement. So we mark it as correct. Now, let's move to the statement in B. If E is open, then f of E is open. Is this a true statement? No, this is a false statement. We can easily find counter example. For example, let f from close interval 0, 1 to R defined by f of x equals to 1 for every x belongs to close interval 0. Okay, that is f is a constant function. Now, since E subset of close interval 0, 1 and our function f maps every element of closed interval 0, 1 to 1, so this function also maps every element of E to 1. So the image of set E under F is, that is f of E is equals to singleton set 1. Okay, and given that E is open, okay, so the function f maps open subset of closed interval 0, 1 to this singleton set 1. But we know that singleton set are closed subsets of R. So this singleton set containing 1 is a closed subset of R. So this implies f of E is closed subset of R. Okay. Thus, if E is open subset of closed interval 0, 1, we can take any open subset. For example, we can take E equals to open interval 0, 1. Okay. E equals to open interval 0, 1. Then too we have f of E equals to singleton set containing 1, because f maps every element of closed interval 0, 1 to 1. So f maps every element of E to 1. So f of E is a singleton set containing 1, and which is a closed subset of R. So we see that even if E is open, f of E need not be open. So the statement in the B is not always a true statement. So we mark it as incorrect. Okay. Now let's move to the statement in C. The statement in a C is, if E is a countable union of closed sets, then f of E is a countable union of closed sets. Is this a true statement? Yes, this is a true statement. Observe that if a set can be expressed as countable union of closed sets, then it is called F sigma set. Okay, a set which can be expressed as countable union of closed sets, then that set is called F sigma set. Here E is a countable union of closed sets, so this implies E is F sigma set. Okay, and there is a property of continuous function which states that continuous function maps F sigma set to F sigma set. So this implies the image of E under F is also a F sigma set. Okay, and by definition of F sigma set, this implies F of E is a countable union of closed sets. Okay, thus if E is a countable union of closed sets, that is, if E is a F sigma set, then F of E is also a countable union of closed set. That is, F of E is also F sigma set. Thus, the statement in C is a true statement. Okay. There is a task for you. Prove that continuous function maps F sigma set to F sigma set. The proof of this property is very easy and short. You can easily prove it. If you get any problem in proving this property, then you can ask me in the comments. Now, let's move to the statement in D. The statement in D is, if F is injective and E is a countable intersection of open sets, then F of E, that is image of E under F, is a countable intersection of open sets. Is this a true statement? Yes, this is also a true statement. This is a little bit tough to prove, but we will prove it. Please don't skip this part of the video because this concept is very important and it can be asked in CSIR NET, GATE. In fact, it can be asked in a PhD interviews of IITs, CMI, TIFR, etc. So please don't skip this portion of the video. So let's prove it. We note that a set which can be expressed as countable intersection of open sets is called G delta set. A set which can be expressed as countable intersection of open sets is called G delta set. Here it is given that E is a countable intersection of open sets. So from this we have E is a G delta set. Okay. But E is a subset of closed interval 0, 1. So this implies complement of E in closed interval 0, 1. That is, closed interval 0, 1 minus set containing E is F sigma set. Because this is a G delta set, so its complement is F sigma set. And we know by definition of F sigma set that we have seen in a statement C that a set which can be expressed as countable union of closed sets is called F sigma set. So as this is a F sigma set, so this implies the complement of E in closed interval 0, 1 can be expressed as countable union of closed sets. Okay, can be expressed as countable union of closed sets. Kn is closed for every n by definition of F sigma set. Okay. Now, note that this is contained in closed interval 0. That is, complement of E in closed interval 0, 1 is contained in closed interval 0, 1. Why? See here. This is closed interval 0, 1. Okay. And E is subset of closed interval 0, 1. Say E is this set. Okay. So what will be the complement of E in closed interval 0, 1? This portion. Okay. And clearly we can see that this portion is contained in closed interval 0, 1. So complement of E in closed interval 0, 1 is contained in closed interval 0, 1. So this implies Kn is subset of closed interval 0, 1 for every n. But closed interval 0, 1 is a bounded set. So we have Kn is also a bounded set for every n. But Kn is closed for every n. Thus we have Kn is closed and bounded set for every n. So this implies Kn is compact subset of closed interval 0, 1 for every n. Okay. Now we will use this equation. From here we can write E as E equals to complement of this union in closed interval 0. That is closed interval 0, 1 minus union n varying from 1 to infinity Kn. Okay. Now we will use the injectivity of F. As F is injective function, so F is bijective onto its range. Okay. As F is injective function, so F is bijective onto its range. From here, operating F on both sides, we get F of E equals to F of this whole term, that is close complement of this union in closed interval 0, 1. Okay. And this can be written as okay, that is, this can be written as complement of this in F of closed interval 0. Why? Because we know that F is bijective onto its range, because F is injective and hence F is bijective onto its range. And we know that for a bijective function, image of complement is equals to complement of image. Okay. For a bijective function, image of complement is equals to complement of its image. So we have this. Now we can write this as, note that A minus B, that is complement of B in A, can be written as A intersection B complement. Okay. So I can write this as A minus B as A intersection B complement. So I can write this as F of closed interval 0, 1 intersection complement of this whole union. Okay. So what will be the complement? Intersection over n varying from 1 to infinity complement of F of Kn. Kn is subset of closed interval 0, 1. Okay. And Kn is a compact subset of closed interval 0, 1. Okay. So image of Kn is a subset of R. So F of Kn is the subset of R. So what will be this complement? R minus F of Kn. Okay. So we can write F of E as this. Now note that closed interval 0, 1 is compact set and F is a continuous function, and we know by properties of continuous function that continuous function map compact set to a compact set. So F of closed interval 0, 1 is a compact set, and as it is an image set, so it is a subset of R. So F of closed interval 0, 1 is a compact subset of R, And we know that a compact subset of R is closed and bounded. So it is a closed subspace of R. And we know that a closed subspace is a G delta set. Okay, so it is a G delta set. We note that this is a G delta set because every closed subset is a G delta set. Every closed set is a G delta set. Now let's look at this term. Kn is a compact subset of closed interval 0 n for every n. Okay, and f is a continuous function. So f maps compact set to a compact set. So f of kn is also a compact set. But kn is a subset of closed interval 0, 1. So f of kn is subset of R. So f of kn is a compact subset of R. And we know that compact subset of R are closed and bounded. So f of kn is closed also or and bounded too. So f of kn is closed. So complement of f of kn in R is open because f of kn is closed. So complement of f of kn in R is open. So this whole set is open. Okay. So we can see that this is a countable intersection of open sets. Okay. And as this is a G delta set, so this is also a countable intersection of open sets. So overall, whole right hand side is a countable intersection of open sets. So we can see that f of E can be expressed as countable intersection of f of E can be expressed as countable intersection of open sets. That is, f of E is a G delta set. So the statement in D is also a true statement. So we mark it as correct. So this is the solution. The correct answer to this question is statement A, statement C, and statement D are true statement. Only false statement is statement B. So if you found this video interesting and helpful, then please like and share this video and subscribe to our YouTube channel. Thank you for watching.